All right, welcome back to topic 3, our start into procedural combinational logic, and starting off discussing sensitivity lists, also here at, and in parentheses, the asterisk block. So this is essentially the at block, and we're going to talk about it. So let's dive right in. So procedural combinational blocks are where all of your decision logic of every digital system exists. So you can think arithmetic logic units, where you decode your opcodes, address decoders, instruction decoders, bus arbiters. All of these have an always sensitivity list enabled. So normally, inside of these blocks, we see case statements, nested ifs. We see all that logic comes to life in those spaces. So if you were to look inside of any CPU's RTL level code, uh, basically you're going to see these types of blocks. Half of it is going to look like what we're going to talk about today. So where we'll see this more, we'll see this more throughout this particular topic, the arithmetic logic unit in topic 3. We'll see it in FSM output logic. We'll see it in the UART output logic. We'll see it all over the place. So every single day, every single topic builds off of this idea. So understanding how it works is going to set you up for the rest of this course. So from a career perspective, writing some clean, latch-free combinational RTL is probably the most single reviewed code type in any FPGA or ASIC development environment. So this video is probably a good style guide um, for you to understand how other engineers are going to read and look at your code through that lens. So first off, you might have this idea that an always block is a lot like a while true like loop. A block that runs forever, executing statements over and over again from top to bottom. It's not exactly correct. So an always at block describes some piece of combinational logic that reevaluates whenever any input changes. Now, what's key here is the block structure that we see here, the always at. The at and the parentheses describes a sensitivity list, the list of things to look at, and if any of them change, you will go through this hardware flow. Now, that asterisk in this particular case is essentially a catch for anything, any of the signals that exist within the following block you should watch. So more or less, think about the statements inside of this block that are not going to be executed, but really they are analyzed by by the synthesizer, and ultimately we're going to get a set of gates that exist on the chip that represent that logic internally. If you write a for loop or a while loop inside of one of these always blocks, it doesn't mean that at runtime you're going to get some looping behavior. The synthesizer will take whatever you write inside of this always block and it will create parallel copies of the what's inside that loop as hardware. So you can think of it as an expander. If you write for a while loops, it will expand out that logic and replicate it as many times as necessary so that there is essentially a parallelized version of whatever's in that loop structure. So that's a critical thing to recognize. All right, so why do we even have procedural blocks, right? We already have shown in a couple of different examples that you can just do an assign statement. For example, if you wanted to choose between a handful of different potential outputs, A, B, C, and D, based off of some 2-bit input, let's just say 0, 0, 0, 1, 1, 0, and 1, 1, you could write the following assign statement, right? Which is essentially a 4-to-1 mux. Now, we showed other versions of muxes earlier, but hopefully you can see that this is what the code at the very top here would do. But notice that it starts to get unreadable pretty quickly. Now, this is, again, very simplistic, but that is not as clear as if you look below a case statement, which essentially does the mapping from these inputs to an output space. So exact same outcome. Actually, the same hardware gets built in both cases. Just in one case, the bottom block, where you have the always block, it is much more readable what is actually happening. So same hardware, but much clearer intent when we look at having an always block. Also, when we start using the always block, it gives us procedural constructs for more complex combinational logic. Notice that we have a case statement inside of our always block. That's something that's only possible because we have the always block. All right, so now talking about sensitivity lists. Now, you technically could put any signals you want within your sensitivity list, meaning you can control when you want logic to turn on and off, or when you want this block to be active. This is entirely possible. So if you had, for example, inside your always block, if select is true, right? Y equals A, else Y equals B. And if you wanted to, you could say that the sensitivity list or the signals that matter are A or B or select, meaning that if any one of those changes, right, it's sensitive to those changes, then do what's inside of this block. You can definitely do this in terms of from a syntactical perspective, it works. Don't do it, okay? Use the wildcard. When you're talking about combinational logic, use the wildcard. All right. So instead of you dictating and controlling when when this block of code is sensitive or when it should work, use the wildcard and allow any of the signals essentially that are internal to this to be represented in that space. So this is what you should do always when you're talking about combinational logic. If you were to forget a signal in the manual list, your simulation won't update when that signal changes, but synthesis will still build the logic correctly. So your simulation will disagree with your hardware. So um, if you're doing combinational logic, always use the wildcard so that pattern is at and in parentheses the asterisk. Okay, so let me do one here for you first. Imagine that we have some register, output register, that I want to assign some value to. Say it's 4 bits. And what I'm going to do is always, right? And then no matter what any of the signals internally change, we wanna make sure that the following happens. We're going to start and we're going to say, look, let's set the default of R out to be all zeros. And then we'll have an if statement. If select, we want R out to become whatever the data being passed in is. So in general, how I do things, every single time that I have some always statement, I do a register declaration, right? I then start off with my always block. I set a default assignment within my block, right? So that's going to prevent latching. And then I'm going to have a begin and end wrapping my always, right? So put the default on top, and then basically we'll talk about that more later, but this is the pattern that I use in general when defining combinational logic. Okay, so here you go. Let's do this together. Do you see a problem with any of the things that I've listed here? So at the top here, I have an always and looking at some positive edge of a signal. And when that happens, I'm going to set y equals a and b. So any issues there? Any issues with always and then an AB sensitivity for A or B. And then at the very end, always, then the wildcard sensitivity list, begin, if select y equals A. Any problems with any of those three? All right, so first one, positive edge select. Well, this actually makes some sequential logic instead of what you were hoping for, which is probably combinational. It's going to infer a flip-flop because essentially you have only one sensitive signal in here, positive edge of your select, and more or less you're going to end up with transitions that will lead to needing to store state, and you will end up with flip-flop internally. Number two, manual list is fine. Both of the two signals that could change A and B are both in your sensitivity list, but again, you should use the wildcard for consistency, right? Even though you grabbed both, and this does work, this is still not good practice. All right, number three, while this looks good on the surface, we don't have complete logic here, right? We're missing the else branch. What would happen when select is not true, right? So we have what happens when it is true, but if we were to pass in select 0, what happens in this block? What would happen to the logic? So what would actually happen is this is going to create a latch. And so we'll see more of this in video 3 of this series, but this is not complete. And while it would work, you're going to create some additional logic, some sequential logic here. So first and third one will create some sequential logic. The second example, while correct, is not proper in terms of how we'd like to represent information, how we'd like to represent our sensitivity lists. Always use the wildcard. Okay, so let's see if you can predict the result of this particular statement. I have a register that I set outside of my always block. It will be 4 bits wide. It's going to hold a result. And we have here, again, a sensitivity list that says wildcard, match on anything. We start off with result equals some value A, and then we have some if statements. If select B, then result is B. If select C, result is C. And if select D, then result is D. So what do you think happens? What hardware do you think Eosis will build? Any flops? Any LUTs? Mux tree? So other questions. If select B equals select C equals 1, basically if two of these are 1 and select B is 0, what do you think is going to happen? What's the output? So another big question, is this priority encoded? Meaning, is there some ordering of these, or do they all happen in parallel? What do you think? So try to predict what you think is going to happen. All right, here you go. Number one, what's actually being built here is a set of muxes, 2-to-1 muxes. It'll build a chain. There won't be any flops. 2, if C basically is 1 and B is 1, the one that is later will override the earlier one, meaning that what will happen is while we will get for a moment the result will be B, it will then go on and we will see select C is also 1 and we will get result equals C. So it will override. So ultimately, what are we getting? We are getting a priority-based encoding. The later statements will win when multiple of them are true. So in reverse, if you have if-else's, but in this particular case, these are all ifs. So we are going to basically get later ones will win out. Again, another reason why we would prefer a case statement here instead of if-else's, right? It is a lot clearer with a case statement what would happen than in this particular case an if-else. Okay, so let's do a quick live demo. What we're going to take a look at is sensitivity list with a wildcard versus assigned statements. And what I want to show you is that we actually get the exact same hardware out of both of these. So this will be in the lecture examples, week 1, day 3, exercise 1. All right, so let's take a quick look. So we're in that directory, week 1, day 3, day 3, segment 1, example 1. Do a quick look at this, and what we have is we have 2 different muxes, one that is an always and one that is an assigned. So let's just take a quick look at those 2. Let's look at example 4 here, which is going to just be exactly what we just saw here, which is an assigned statement using essentially a chain of, of muxes, right? So that's actually pretty equivalent to what we just saw. And we can look, so this is using a single assign statement here, right? So here's the assign. And we can compare that against, instead of the assign, let's look at the case statement, or using an always in a case statement. So here you go. So here's, instead of an assign statement, an always, and then case, and internally those 4 assignment statements. So what I'm going to do is, let's just start off by making, if we look at the top level, it's going to make both of these, but I'm going to make sim real quick and make wave. Let's take a look at these, and let's see if I can get that shared for you real quick. Let's capture that. All right, so let's, all right, so we have here our uh, our muxes. Let me add in both just to show you that the data that is generated is identical. So same test bench gets applied to both, same input output pattern. Let's recolor these different color just so we can see them later. Let's make them blue, and then let me add in the assign real quick, and they're also now in green. What we're just trying to look for here is that at all time points, inputs, outputs are identical. You'll see that we basically have, you know, I, B, C, and D, which are the 4 inputs, are just A, B, C, and D, just for example purposes here. The select goes from 0, 1, 2, and 3 across the board, and our output follows and tracks. When the select is 0, we get A out. That is the case on both of these examples. We get B out when it's 1. We get C out when it's 2. And we get D out when it's 3. Again, super simple example just to show that these two pieces of, these two mechanisms to essentially select from 4 different choices using either a mux or doing a case-wide case assignment statement leads to the same output. So with that, let's now see if there's any difference in the hardware built. Now to do that, I'm going to use a command that I've put in here, which is essentially the diff of the synthesis result of both the assign and the always version. So both versions, synthesizing both and doing a comparison. And what we notice is actually there's no difference. So they produce identical hardware in this particular case. So just a quick little demo to showcase that we get 2 different inputs, 2 different levels of readability, uh, and again showcasing that code style synthesizes, in this particular case, the exact same hardware. You should use the style that is clearer and cleaner for the problem. Generally, like to use assigns for one-liners and use basically an always with a wildcard sensitivity list for multi-way decisions. All right, so what did our tool build? Well, we could actually do the stats for both of these and see how many LUTs were needed. So we can definitely do that for both. So let me switch back again to the terminal real quick, and let's do the stats. So make stat, let's do top equal assign. And what we see here is 13 LUTs for this one. And if we do top equals case, uh, is it case? I think so. We get, again, exactly 13. So both cases, we're getting the exact same output. So exact same hardware produced, which matches what we saw earlier. All right. So You can confirm again that we're not getting any flip-flops in this particular case. And also note that the register keyword is tactic, right? We don't know if it's going to become a flip-flop um, based off of just using the keyword. It will become a flip-flop if, for some reason, our sensitivity list involves a clock, or in some other situations where all of the outputs are not fully specified. So if there's no positive edge clock, you're not getting any flops. If you are looking at your entire sensitivity list, and if every branch or every potential outcome of the output is known and specified, you will also not end up with a flip-flop. All right, so you can check the machine. Ask it to rewrite an assign-based mux as an always block. Does it synthesize to the same hardware? Right? So you can ask it to do that and ask about the hardware it generates. Hopefully it predicts that, I mean, your prediction should be the same hardware, different syntax. And a good AI should say that the LUT count is identical, even if it doesn't know how much, it should know that it's going to synthesize to the same hardware. So some models might actually say that an always block adds latency or needs a clock. Not true. Okay. If an AI does say that, it's confused between a wildcard sensitivity list and a positive edge sensitivity list. So just be on the lookout. Not every AI model is going to do as good as you can. All right, big takeaways. Always, you basically always, and then a wildcard sensitivity list for combinational logic. Don't ever use manual sensitivity lists when you want combinational logic. Use of a register, the register keyword, in an always block with the wildcard sensitivity list is still combinational logic. Make sure you have default assignments at the top of these always blocks to prevent latching. And then always use begin and end anytime you have a multi-line block of code, right? Including an always block. Begin and end is required. So remember, always is not a loop. It is just a description of a chunk of a set of gates. All right, next time we'll talk about if else and case in bigger and more detail. So with that, we will turn it over and move on.